Now let's construct the operator Sx. For this we make use of the relation A is equal to sum over A prime lambda A prime. A prime are the eigenvalues of A, right? A prime are the eigenvalues of A, and lambda A prime is the projection operator. Get A prime, bra A prime. Alright. Now we have seen that this happens if we use the eigenkets of this operator itself as the basis. Alright, we could use the eigenkets of the same operator as basis, and then the operator has a simple form like this. We could do the same thing with Sx, right? The Sx operator. So we have to take the eigenkets of the Sx operator. We know that the eigenkets of Sx operator are Sx plus and minus. Okay, the eigenvalue equation can be written as Sx acting on Sx plus minus is equal to plus or minus h bar by 2 Sx plus minus. Right, this means that we have got two eigenkets here, Sx plus and Sx minus. One corresponds to the eigenvalue plus h bar by 2 and the other to minus h bar by 2. So what we do is that we can first write Sx in terms of these eigenkets, right? Sx plus and Sx minus. So we use the same expression here. We can write Sx is equal to sum over the eigenvalues. There are only two eigenvalues here, right? So we take the first eigenvalue plus h bar by 2 and then the projection operator Sx plus get Sx plus bar Sx plus, all right, and then you take the next eigenvalue because you have to take the eigenvalue here, right? You have to multiply the eigenvalue here minus h bar by 2 and then I have got get Sx minus bar Sx minus. All right, so that's what we have here. Sx equal to, I can take this h bar common outside, okay, and then I can write Sx equal to h bar by 2 Sx plus okay, get Sx plus bar Sx plus minus get Sx minus bar Sx minus. All right, now I can make use of the what is the expansion of Sx plus in terms of the eigenkets of Sz. All right, so we are using this as the basis now. We are using this as the basis. Okay, we are using this as the basis. We expanded Sx plus and Sx minus in this basis already. All right, so we would like to have the operator Sx in the same basis. All right, or the matrix elements of this operator in the same basis. Okay, we can do this. We just need to make use of these relations. All right, Sx plus equal to 1 by root 2 get plus 1 by root 2 e raised to I delta 1 get minus, and similarly for Sx minus. So we take these expressions, find the corresponding bars, and then substitute it here. It will boil down to an expression like this. We'll get Sx equal to h bar by 2 e raised to minus I delta 1 get plus bra minus plus e raised to I delta 1 get minus bra plus. All right, so let's see how we can do this. Now this is the expression for Sx that we need to simplify, all right, or we need to write in terms of get plus and get minus, or the eigenkets of the Sz operator. All right. So for this we make use of this expansion. We have already expanded get Sx plus in the basis of the eigenkets of Sz. All right, in the basis formed by the eigenkets of Sz. All right, or in the basis spanned by get plus and get minus. These expansions are given here. So we just make the substitution here, all right, and then you combine them, we'll get the expression for Sx in terms of get plus and get minus. That's what we need. So let's do this. The first term here is get Sx plus bar Sx plus. So first let's write get Sx plus, and the first term, right, get Sx plus. This is get Sx plus is 1 by root 2 get plus 1 by root 2 e raised to I delta 1 get minus. Okay, now we have to multiply it with the corresponding bra. We know how to find the corresponding bra. It is 1 by root 2 bra plus 1 by root 2 e raised to minus I delta 1. Right? When you go to a bra space, these numbers become the complex conjugate, or in general I becomes minus I. We already said that delta 1 is real. So this is e raised to minus I delta 1 and bra minus. All right. Now you can multiply this. There will be 4 terms. Let's do this. We have to combine each term here with every term or in the next bracket. All right. So we have got, we'll have to take this combination first. So we can multiply the numbers together. That will become plus 1 by 2. Then I've got get plus bar plus. Okay. I have to multiply this with this here. That becomes 1 by 2 get plus. Sorry, there is also this e raised to minus I delta 1. Let me write that first. And then I've got get plus bra minus. Okay. Now let me take the next multiplication. It's 1 by 2 e raised to I delta 1. All right, I'm taking this multiplication, so it becomes 1 by 2 e raised to I delta 1 ket minus bra plus, okay, and then plus we do this multiplication, it is equal to 1 by 2 1 by 2 e raised to I delta 1 multiplied by e raised to minus I delta 1, that is 1. So this becomes ket minus bra minus. Okay, what is this? This is the first term in this expression. This is the first term here. Right? This is ket sx plus bra sx plus. All right. Let's also find ket sx minus bra sx minus. All right. So I'll write it here. Get this term. Right. I'm writing down this term. So first I write ket sx minus, which is given here. It is 1 by root 2 ket plus minus 1 by root 2 e raised to I delta 1 ket minus. All right, so this is ket sx minus here. Now you multiply this with the corresponding bra. We know the rule. This becomes 1 by root 2 bra plus minus 1 by root 2 e raised to minus I delta 1 bra minus. All right. Okay, now let's do the same multiplication. We get 4 terms. We get 1 by 2 ket plus bra plus, okay, and then we get minus. All right, this, when I combine this, there's a minus sign here. This becomes minus 1 by 2 ket plus e raised to, sorry, I missed this. So when I combine this, there's also this e raised to minus I delta 1. So this becomes minus 1 by 2 e raised to minus I delta 1 ket plus bar minus. Okay, now the other terms minus 1 by 2, right, minus 1 by 2. When I combine these two terms, it becomes what is it, ket minus bar plus. Okay, and there's one more term, it becomes plus 1 by 2 e raised to I delta 1 multiplied by e raised to minus I delta 1 is 1. So there was just 1 by 2 here. This minus and this minus cancel, so it's plus 1 by 2. This is ket minus bar minus. All right. Now what is this? This is the second term in here. All right. So let me write this as equation 1 and this as equation 2. Okay. Now in order to find this result, what we need to do is we need to find 1 minus 2. Okay. The first term is written here. Right? The second term is written here. Right. So we have to subtract these terms. So what happens when we subtract? Let's see here. There's this half ket plus bra plus here. There's a half ket plus bar plus here. So when you subtract, these two terms cancel. Okay. Let's see if there is any other term that cancels. There's a half ket minus bra minus here. There's a half ket minus bra minus here. Same term. So when you subtract, they also vanish. What about the other two terms? There's half e raised to minus I delta 1 ket plus bra minus. There's a corresponding term here, ket plus bra minus, but with an opposite sign. All right. So when you subtract this from this, right, this term minus this, it will become plus, and the rest of the terms are exactly the same. Right? So this is just twice this term. Right. I hope this is clear. We are subtracting this term. We are subtracting this term, right, from this term here. Okay. So when I subtract, since this is a minus sign, when I subtract this term from this, it becomes an addition. Okay, and half plus half is 1. The rest of the terms are same. So this becomes e raised to minus I delta 1 ket plus bra minus. Okay, there's one more term here, half e raised to I delta 1 ket minus bra plus and minus half ket minus half ket minus bar plus. All right, again when I subtract this term from this term, this minus will become a plus and I get plus e raised to I delta 1 ket minus bar plus. Okay, what is this? This is the term in the bracket here, right? This is the term in the bracket here. What is Sx? Sx is simply h bar by 2 multiplied by this, right? So we can write Sx is equal to h bar by 2 multiplied by, okay, h bar by 2 multiplied by e raised to minus I delta 1 ket plus bra minus, which is this, and e raised to I delta 1 ket minus bra plus, right? E raised to I delta 1 ket minus bra plus, which is this. Okay, what have we done here now? We have got operator Sx in terms of the base kets of Sz, right, or in terms of the eigenkets of Sz, eigenkets and eigenbars of Sz. Right. Now we can make use of these things. We can make use of this operator. Okay. All right. Now this is what we found. Sx is equal to h bar divided by 2 e raised to minus I delta 1 ket plus bra minus plus e raised to I delta 1 ket minus bra plus. Right. Now you can verify whether this is actually Hermitian. We need our observables to be Hermitian operators. You can see that this is actually Hermitian. Okay. So how do you check whether this is Hermitian? You take S dagger and see if this is equal to Sx. Okay. We can do that here because when I take the Hermitian conjugate of this term, right, the complex numbers become the corresponding complex conjugate. So this term would become, when I do the dagger, this term becomes e raised to I delta 1. All right. And what happens to bras and kets? We have seen that if you have ket alpha bra beta, an operator like this, the complex conjugate of this is actually bra beta ket alpha. Right? We have actually proven this in one of our previous classes. Okay, you can check the notes. So this means that this term is e raised to I delta 1 ket minus bra plus. Okay, what happens to this term when I take the the Hermitian conjugate? This becomes e raised to minus I delta 1. Okay, ket plus bra minus, again using this rule. Okay, so let's find Sx dagger. Sx dagger is h bar divided by 2 multiplied by this. Right, now we can just rearrange this h bar by 2. I can write this term first. This is e raised to minus I delta 1 ket plus bra minus plus e raised to I delta 1 ket minus bra plus. Okay, which is exactly Sx. We see that Sx dagger is equal to Sx, or in other words, it is Hermitian. Right? We just made use of this rule, and as I said, we have already proven this, so I am not going to prove it again here. Okay. Now we got ket Sx plus minus and operator Sx. Right? The arguments for the case of Sy are also exactly the same. Right? So you carry out exactly the same arguments that we used to determine Sx plus minus and operator Sx. All right, we'll see that Sy plus minus has exactly the same form. It's 1 by root 2 ket plus minus 1 by root 2 e raised to I delta 2 ket minus. All right, so instead of delta 1 over there, I'm using delta 2 here. That's all. Right? And Sy operator again has the same form. It's h bar by 2 e raised to minus I delta 2. Instead of delta 1, I have delta 2. That's all. Right? E raised to minus I delta 2 ket plus bra minus plus e raised to I delta 2 ket minus bra plus. Okay, this is operator Sy. Okay. Now you can just use the same arguments that we did in the case of ket Sx plus minus and operator Sx, all right, to find these operators. So maybe you can do it as an exercise just to convince yourself. Okay. We found the states Sx plus minus as well as Sy plus minus. We also got operators Sx and Sy. Right? But there's a small problem. There are two constants which are undetermined yet. Right? We saw that there are delta 1 and delta 2 in the phase factors, the real numbers. These are not determined yet. So next question is there anything that we can use to determine delta 1 and delta 2? Right, now actually there is one information that we have not yet used. Let's see what we can do about it. Let's see what relation we can use to find delta 1 and delta 2. Okay. Alright, so this is the situation. We can consider a sequential Stern-Gerlach experiment with Sg x hat followed by Sg y hat. Right, so let's put it here. We have got an Sg, let's say Sg x hat apparatus. So right, a beam of atoms are coming into an Sg x hat apparatus. Right, and we know that there will be two outputs, plus h bar by 2 and minus h bar by 2. Okay, so what I do next is, you know that there are two outputs, one set of beams characterized by Sx plus and another set of beams characterized by Sx minus. Right, what I do next is then I can use two more Stern-Gerlach apparatus. This time I am using Sgy hat, right? And I am feeding this Sx plus beam, right, a beam characterized by Sx plus, into an Sgy hat apparatus. What do you expect? Naturally, you expect two beams coming out of it. Okay, one corresponding to eigenvalue plus h bar by 2 and the other corresponding to eigenvalue minus h bar by 2. Or In other words, if I send in this Sx plus beam into an SGY hat apparatus, what I expect is that I'll get a set of atoms which are characterized by Sy plus and another set of atoms characterized by Sy minus. Okay, the same thing happens if I feed the second beam into an SGY hat apparatus. So that I could do the same thing with an Sx minus beam, right, or a beam of atoms characterized by Sx minus. Again, I can send it into an SGY hat apparatus, and I get a beam characterized by Sy plus and another beam of atoms characterized by Sy minus. Right? We could actually carry out this experiment, and this is the result we are going to get. Okay. Now we could also expect that this should be the result. Why? Because we already saw that if I feed this Sx plus into an SGZ hat apparatus, I'll get two beams. Similarly, if I send an Sx minus beam into an SGZ hat apparatus, again I'll be getting two beams. And we said that Sx plus beams have components along both Sz plus and Sz minus. Right? Now these directions are not special. Right? The choice whether I choose X, Y, Z like this or in any other rotated manner, it doesn't matter. Okay, we are talking about, because there's nothing about physics that tells us that one direction is special. Right? So if I send an SGX hat apparatus, if I send an Sx plus beam into an SGZ hat apparatus and get two beams as output, I should also get the same thing if I send it into an SGY hat apparatus. Right? So this is basically the rotational symmetry. Right? So all directions in space are equivalent. All directions in space are equivalent. Right? By what do you say, carrying out an experiment, you shouldn't be able to understand which direction your experimental apparatus is pointing, whether it's in the y hat or in the z hat direction, right? So these are coordinates that we choose for convenience, x, y, z, right? So from rotational symmetry or from isotropy of space, we expect that the same thing should happen with SGY hat apparatus also. Now, if this argument is not satisfactory, we could just carry out the experiment, and the result will be, as I said, the result will be that if I sent in a beam of Sx plus atoms into an SGY hat apparatus, I'll get two outputs. Similarly, if I sent in Sx minus beam into SGY hat apparatus, again I'll get two beams. Alright, we can also see that the intensities are the same. Intensities are also equal, which means that the probabilities are equal. This again means that the Sx plus, right, Sx plus beam, or a beam, what do you say, ket Sx plus, right? We characterize this beam by ket Sx plus. This means that ket Sx plus has components both along Sy plus and Sy minus directions. Let me write these kets here, right? So there are equal components along Sx plus and Sy. Sorry, ket Sx plus has components along both Sy plus and Sy minus directions. Okay? So we say that the probabilities are equal. So this means that, so using again the probability postulate that we had, this means that the probability that if I make a measurement of Sx plus, that if I take a beam of Sx plus and measure the spin along y direction, the probability that I'll get plus h bar by 2, the probability is plus half, and the probability that I'll get minus h bar by 2, this also is half. Okay, so according to the probability postulate, this is how we calculate the probability. You take the Sx plus beam and you project it onto a direction Sy plus and Sy minus. Alright, and if I take the modulus square, I should get 1 by 2. Alright, because these are equal probabilities and there are only two possibilities here. So if modulus square is 1 by 2, this means that the modulus has to be 1 by root 2. Okay, so if I take Sx plus and I project it onto Sy plus minus, I should get 1 by root 2, and take modulus, of course. All right, and if you take the modulus, you should get 1 by root 2. Similarly, if I take Sx minus, right, again, because Sy minus going into an SGY hat apparatus returns two beams with equal probabilities. This means that Sx minus has a component also along Sy plus and minus directions, and since the probabilities are equal, according to probability postulate, modulus of this component is equal to 1 by root 2. Because according to quantum mechanics, modulus square is the probability, which will give you 1 by 2. All right. Now this is not surprising in view of the invariance of physical systems under rotations. This is a basic fundamental symmetry of nature. All right. You might have already discussed this rotational symmetry, etc. This means basically that by pointing our apparatus in different directions, all right, we should get the same result, because all directions are equivalent. All directions are equal in space. There's no preferred direction in space, so to speak. There's no preferred direction in space. We say that space is isotropic. Right? So I hope this is clear. The argument is clear. Either from experiments or from this rotational invariance argument, we know that these relations have to be satisfied. All right? We have also used the probability postulate. Okay. Now we can demand this thing. Right? We have got get Sx plus and we have got get Sy plus. Right? So we can demand these relations, and from these relations we might be able to find delta 1 and delta 2. Okay, at least we'll find the relation between delta 1 and delta 2. Okay, so this is the set of relations that we are going to make use of. Okay, this is equation 5 from the previous slide, and we have got get Sx minus and get Sy plus minus here. Right? So we can make use of these relations. Let's see how this works. All right, let's first find this relation. All right, let's check this relation. Let's just find Sy plus bra Sy plus get Sx plus. Okay, get Sx plus. Or I have got get Sx minus here. Let's do get Sx minus. Okay, let's first find this and then we'll take the modulus. Or maybe we can take the modulus from the beginning. So this is equal to modulus of, all right, modulus of, what do I have here? This is bra Sy plus. Okay, and Sy plus is given here. So let me write bra Sy plus here. That becomes 1 by root 2 bra plus 1 by root 2 e raised to minus I delta 2 bra minus. Okay, I've just found the corresponding bra for Sy plus, for get Sy plus. Okay, multiplied by, okay, get Sx minus, which is written here. Okay, this is 1 by root 2 get plus minus 1 by root 2 e raised to I delta 1 get minus. Okay, we need to take the modulus and we demand that this modulus is equal to 1 by square root of 2. Okay, now this is equal to, let's make the combinations. We see that bra plus combines with bra plus to give 1, bra plus combines with bra minus to give 0, sorry, bra plus combines with get plus to give 1, bra plus combines with get minus to give 0, bra minus combines with get plus to give 0, bra minus combines with bra minus to give 1. These are the orthonormality relations. Okay, maybe I can write it down. This is 1. Okay, bra minus get minus is also 1, but these combinations, these cross terms are 0 by orthonormality or orthogonality. These are eigengets corresponding to different eigenvalues. They are orthogonal. And we proved this in the fundamental theorem. Alright, now we take the combinations here. This means that 1 by 2, we need to take only the non-zero combinations. 1 by 2 plus 1 by 2 e raised to, there's this minus I delta 2 and I delta 1. I can take this I outside and then delta 1 minus delta 2. Okay, and we also have this modulus here. So modulus of this thing is equal to 1 by root 2. I can pull this 1 by 2 outside because that's a real number, and then I have got this is a real positive number. Okay, so this is 1 plus e raised to I delta 1 minus delta 2. Okay, the modulus of this has to be equal to 1 by root 2. Okay, I have made use of one of the relations. You can make use of the other relation. Actually, you could find the what do you say here? This is what we did. You could do the same thing with minus also. All right. And we will see that you can also get another relation with the minus sign here, with the minus sign here. Right? So this is the condition. This condition boils down to 1 by 2 modulus 1 plus minus plus or minus e raised to I delta 1 minus delta 2 is equal to 1 by square root of 2. Okay. Now this means that, okay, 1 by 2 multiplied by modulus of a number is 1 by square root of 2. This means that modulus of this number has to be equal to square root of 2. Right. This means that, let me make some space here. Now this means that modulus 1 plus minus e raised to I delta 1 minus delta 2. Okay, modulus of this has to be equal to, I can multiply by 2 on both sides. This has to be equal to square root of 2. Alright. Now here I already have the real part of this complex number equal to 1. Okay, I need the modulus of this to be equal to square root of 2, right? Which means that the imaginary part also has to be 1. Right? So how do we find the modulus of a complex number if we have z equal to a minus b? This means that square root of a square plus b square, square root of a square plus b square is equal to, this is what we call the modulus of z, right? So here what I have is the square root of real part square plus imaginary part square is square root of 2. Okay, this means that real part square plus imaginary part square is 2, or the imaginary part is 1. The imaginary part has to be equal to 1. It could be plus or minus 1. Okay, so when do I get e raised to I delta or e raised to I phi, some constant equal to 1? Right, this is only when the angle is pi by 2 or minus pi by 2. Right, so whether it's pi by 2 or minus pi by 2, this will work. Why? Because e raised to I pi by 2 is equal to cos pi by 2 plus I sin pi by 2. Okay, and you get this is equal to I. All right, so if it is 1 plus or minus I, this means that the imaginary part here is also 1, and then this condition will be satisfied. Okay, I hope my argument is clear. This means that this delta 1 minus delta 2 should either be equal to pi by 2 or minus pi by 2. Right? It should either be plus pi by 2 or minus pi by 2. Okay, so let me repeat. If this modulus of this is the modulus of a complex number, if this is square root of 2, and the real part is 1. All right, so real part is 1. So what we need is square root of the real part square. Let me write real part square plus imaginary part square. This has to be equal to square root of 2. Right? This means that real part square plus imaginary part square is 2, which means that imaginary part. So if real part is 1, right, this means that imaginary part also has to be equal to 1, which again means that e raised to I delta 1 minus delta 2 has to be equal to 1. It could be plus or minus 1. And this happens for delta 1 minus delta 2 is equal to plus or minus pi by 2. Okay, that's how we found that. Now we have a relation which says that delta 1 minus delta 2 or delta 2 minus delta 1 is equal to pi by 2 or minus pi by 2. Okay. Or we can write delta 2 minus delta 1 is pi by 2 or minus pi by 2. Okay. We thus see that the matrix elements of Sx and Sy cannot all be real. Why is that? We have found that delta 1 minus delta 2 must be related in this one, or I think we wrote it as delta 2 minus delta 1. It doesn't really matter. This is either pi by 2 or minus pi by 2. Okay. This means that the difference between these must be equal to pi by 2 or minus pi by 2. Right? Again, if I look at this operator Sx, right, we can find the matrix elements of this Sx in the basis ket plus, ket minus, which are the eigenkets of Sz operator. How do we find the matrix elements? We can find all these combinations. We have got ket plus, ket minus, which are the basis vectors, ket plus, sorry, bra plus, bra minus here. Okay, so we have got this bra plus Sx ket plus, bra plus Sx ket minus, bra minus Sx ket plus, and bra minus Sx ket minus. Alright, these are the matrix elements. These are the four matrix elements. Right. Now suppose this delta 1 is 0 here. Suppose we can choose this delta 1 to be 0. If delta 1 is 0 here, then all these are real. Right. So if, let's say if delta 1 is 0, for example, if delta 1 is 0, then this becomes Sx becomes h bar by 2 ket plus bra minus plus, okay, ket minus bra plus. Okay, this is operator Sx if delta 1 is equal to 0. Now in this case all these matrix elements are real. Right? For example, let's calculate the first matrix element. You have to sandwich this between bra plus and ket plus. So if I put a bra plus and ket plus here, you'll see that it will be 0, because this combination of bra minus and ket plus, that will be 0. Similarly, this bra minus will be killed by the, so this ket minus will be killed by the bra plus on this side because of the orthonormality. Okay, if I look at this element, for example, let's just take this element, right? So I've got h bar by 2 outside. I'm just calculating this matrix element. Okay, I've got h bar by 2 outside. So this is bra plus, and what is Sx? Sx is h bar by 2 is pulled outside. This is ket plus bra minus plus ket minus bra plus. Okay, and what's on this side? It is ket minus. All right. Now if I look at this, Okay, I can combine these terms here. These two will combine. Right, these two will combine to give 1, and this will combine to give 1. Right, so this becomes h bar by 2 multiplied by, this simply gives you 1, plus again you see that this gives you 0. This gives you 0. Why? Because this get minus combines with bar plus to give 0. So you see that this matrix element is simply h bar by 2. This matrix element is simply h bar by 2. Right? Now the point to be noted is that all these matrix elements are real if delta 1 is 0. Delta 1 is 0. All these matrix elements are real. We can choose these matrix elements to be real. Okay, that's fine. But if delta 1 is 0, then delta 2 cannot be 0. But if delta 1 is 0, delta 2 has to be pi by 2. If delta 2 is pi by 2, if you look at this operator here, this term will become minus I and this term will become a plus I. Right? Which means that the matrix elements will not be real. Right? So if I choose the matrix elements of Sx to be real, right, by setting delta 1 equal to 0, that means that the matrix elements of Sy cannot be real because these phase factors here will introduce minus I and plus I here. I hope this is clear. That's the reason why we say that the matrix elements of Sx and Sy cannot all be real. Alright, we'll calculate these matrix elements later on. Let me just repeat this thing. Right? Now, these coefficients appearing here, right? These coefficients appearing here, what we have basically seen is that these coefficients, right, these coefficients appearing here, if these are imaginary, if these are complex, then the matrix elements also can be complex. Right? If this is equal to 1, then the matrix elements can be real. So we might be able to choose the matrix elements of Sx to be real by setting delta 1 equal to 0. Then there are no i's floating around. Okay, there are no imaginary i's floating around here. Right? But if I choose delta 1 equal to 0, that means that by this relation, delta 2 has to be equal to pi by 2. Or minus pi by 2. Right? If I put that here, if I put delta 2 equal to plus or minus pi by 2 here, I'll get the factors of i's floating around here. Right? So if the matrix elements of Sx are real, you cannot have the matrix elements of Sy to be real. Right? So either you should have both matrix elements of both Sx and Sy imaginary. Right? The best we can do is that we can make the matrix elements of one of the operators to be real, and then the other one, the matrix element of the other operator, has to be imaginary. All right. So if the Sx matrix elements are real, the same thing goes in the other direction also. Right? The same argument goes in the other direction also. So if the Sx matrix elements are real, the Sy matrix elements must be purely imaginary. And vice versa. Okay? So just from this extremely simple example, the introduction of complex numbers is seen to be an essential feature in quantum mechanics. We say that the complex numbers must be introduced to quantum mechanics. All right. So the use of complex numbers is in some way fundamental to quantum mechanics. So in classical mechanics, we might have used complex numbers to make the solution more convenient or to manipulate things easily. And in the end, right, we always used to take the real part of it or the imaginary part of it, of the solution. For example, you can solve the harmonic oscillator problem or the damped harmonic oscillator problem in classical mechanics, and the solutions are in general complex. We construct them to be complex so that we can manipulate them easily, and in the end we would take only either the real part or the imaginary part, which are both real. All right. So there we used complex numbers to make things convenient, but in quantum mechanics they enter into the theory in a more fundamental manner. We cannot get rid of these complex numbers. Right? The same is the case. Right? If I look at the eigenkets, for example, Sx plus. If I look at the eigenket Sx plus, I think we wrote this as 1 by root 2 ket plus e raised to I delta 1. I don't remember the exact factor here. I think it's e raised to I delta 1 divided by root 2 ket minus. All right. I could choose delta 1 to be 0, and there won't be any complex number. There wouldn't be any complex numbers appearing in the expression for ket Sx plus. Right? But if I choose delta 1 to be 0, then delta 2 has to be pi by 2, and then you will see that in the case of Sy plus, which is equal to 1 by root 2 ket plus e raised to I delta 2 by square root of 2 ket minus. Okay. In this case, you will see that if delta 1 is chosen to be 0, delta 2 has to be equal to either pi by 2 or minus pi by 2, which means that I'll get a complex number appearing here. All right. So this is how complex numbers enter into quantum mechanics in a fundamental manner. It's an essential feature of quantum mechanics. Okay. Now we are allowed to choose one of the phase factors. We can choose delta 1 equal to 0. Right? The only thing that constrains us is delta 2 minus delta 1 has to be equal to pi by 2 or minus pi by 2. Right? So it's convenient to take SX matrix elements to be real. This can be done as we demonstrated briefly. This can be done if delta 1 is taken to be 0. So it is convenient to take the SX matrix elements to be real and set delta 1 equal to 0. If we were to choose delta 1 equal to pi, right, you could choose delta 1 equal to pi and then the matrix elements of SX would still be real. Okay, but when we study rotations, we'll see that delta 1 equal to pi corresponds to the positive x-axis being in the opposite direction. Right? So these are related by rotations, but we'll be seeing this later on. Okay? So for now, it is sufficient to say that we can choose delta 1 equal to 0, and then the matrix elements of Sx will become real. Right? The second phase angle, delta 2, must be either minus pi by 2 or plus pi by 2. Okay, again, there's an ambiguity here. It could either be plus pi by 2 or minus pi by 2. Right? This ambiguity still exists. Right? But this ambiguity will disappear when we have specified whether the coordinate system we are using is right-handed or left-handed. Okay, so we have not made a choice of what kind of coordinate system we are using. If we are using a right-handed coordinate system, then we'll see that this angle can be pi by 2. But these things we'll discuss when we look at rotations. So we have not yet specified whether the coordinate system we are using is right-handed or left-handed. Given the x and the z axis, there is still a twofold ambiguity in the choice of the positive y-axis. It's true, right? If I choose x and y here, I could choose the positive x-axis to this direction or to the other direction, right? So we'll see that this ambiguity actually boils down to the fact that you could either choose a left-handed or a right-handed coordinate system, okay? Now later we'll discuss angular momentum as a generator of rotations. Okay, this concept you might have heard as so you might have seen these things in classical mechanics, the concept of generators, etc. But we'll be discussing this in a special quantum mechanics context in the following chapters. All right. So later we'll discuss angular momentum as a generator of rotations using the right-handed coordinate system. It can then be shown that delta 2 is equal to pi by 2 is the correct choice. All right. So even though we haven't exactly given all the reasons here, the idea is that we can choose delta 1 equal to 0 and delta 2 equal to pi by 2, and choosing delta 2 equal to pi by 2 corresponds to choosing a right-handed coordinate system. Right-handed coordinate system. Okay. All right. So delta 1, we have used this freedom to set delta 1 equal to 0. All right. But then delta 2 has to be equal to pi by 2 or minus pi by 2, and we choose delta 2 equal to pi by 2, which is equivalent to saying that we have chosen a right-handed coordinate system. We are always using a right-handed coordinate system, not left-handed coordinate system. Okay. Let's summarize our results. We have ket Sx plus minus equal to 1 by root 2 ket plus or minus 1 by root 2 ket minus. Okay, so we take the earlier expression. I think we had the earlier expressions like this. Ket Sx plus minus was equal to 1 by root 2 ket plus, okay, plus or minus e raised to I delta 1 ket minus. Okay, there is a 1 by root 2 here also. I just put delta 1 equal to 0 and I get this expression. Similarly, you put delta 2 is equal to pi by 2 in order to get this expression. Ket sy plus minus is 1 by root 2 ket plus or minus I by root 2 ket minus. Okay, we also have the expressions for operators. We just take the previous expressions and just set delta 1 equal to 0 and delta 2 equal to pi by 2. So the expression for the operator Sx becomes h bar by 2 ket plus bra minus plus ket minus bra plus. Okay, these complex factors have disappeared because of the choice delta 1 equal to 0. Similarly, you see that Sy is h bar by 2 minus I ket plus bra minus plus I ket minus bra plus. Okay, this I comes because I have chosen delta 2 equal to pi by 2, but this minus I also comes because I have chosen delta 2 equal to pi by 2, and e raised to, if you have e raised to I pi by 2, this is equal to cos pi by 2 plus I sin pi by 2, which is equal to I. All right. So we see that the Sx plus minus and Sy plus minus eigen gets given here are seen to be in agreement with our earlier guesses based on an analogy with the linearly and circularly polarized light. So in the beginning, right, we analyzed the results of the Stern-Gerlach experiment, and we saw by looking at the analogy with polarization of light, we actually had guessed how to represent these states. Again, over there also we said that we have to use the complex numbers. Right? Now here we have used the basic postulates of quantum mechanics, probability postulate basically. Right? So we have used these postulates along with the experimental results to determine that these states can actually be represented as we did before. So our guesses were correct. Okay. So with that, we'll conclude this session. Thank you.